Okay, thank you for joining me on this video. Today we're going to have a look at critical path analysis. This is my first video on the critical path analysis series, and what I'm going to be doing today is just explaining a little bit about what critical path analysis is and how it's executed. And then I've got two examples to show you. In future videos we'll consider more complex problems, including ones with dummy arcs and ones that involve cascade diagrams, histograms, and also crashing the network. Just note that for this specification, this is the MwA specification modeling with algorithms, we perform critical path analysis on activity on arc networks, not activity on node networks. Okay, so critical path analysis, what is it? Well, it is an analysis which allows us to decide which activities in a project are critical, essentially, which ones cannot be moved if we want the whole project done in a minimum time. What we often have with the critical path analysis problems is we'll have networks which look like this. All of the arcs will be directed. They will have arrows on them, like so. There'll be one start node, which in this case is this one here, because it's the only node that's got activities coming out of it, and we've got one end node. This is the only node that's got arcs going into it. Each arc represents an activity within the project, and each node is referred to as an event of the project. Now what this network represents is this activity here, for example. This one cannot be started until that one, and that one have all been finished. Okay, so this might be, I don't know, maybe we've got a building project here, and this activity is to do the wiring. And you can't do the wiring until the roof is on, the walls are up, the plasterboard's done, and some other activity that had to have been finished to do the wiring. So this activity cannot be started until all of these have been finished. This one can't be started until this one's finished. So this one can't be started until all five of these activities are done. Essentially, it's what this network is telling us. And then once that activity is done, along with those two, then we can start this activity. But you can't start this one until all three of those have been completed. And the question is, which activities must happen at certain times within the project for the whole project to be completed within some kind of minimum completion time? This is the start node. Any activities that come out of the start node don't need anything to have been done before those can be started. And those that go into the end node, there's no activity which relies on those having been completed to be started. There are many other aspects to critical path analysis, which we will get on to throughout this series. But in this video, we are just going to focus on the algorithm itself. Okay, the critical path analysis algorithm. I've got two networks that have already been drawn. We will look at precedence tables a bit later, which is how we draw the network in the first place. But today we're just focusing on the actual algorithm. Okay, so here we have a network. Not all networks are drawn quite as rectangular as this one, but this one is drawn in a fairly rectangular manner. And to perform critical path analysis on this network, we are going to need to draw a double box next to each event. Okay, just two little squares, one besides the other. And that needs to happen next to every node or every event of the project. This may be already drawn for you in your answer booklet in an examination setting, but of course real life isn't an exam, so you have to draw these on yourself. Now, all of these activities have been labelled with capital letters, which is quite common on this course. So I've labelled them A to M, to A, B, C, D, E, F, G, H, all the way up to M. And then also there's a number in the brackets after each of these activities, and that represents the duration that activity needs to to be completed. So for example, activity B takes 10 units of time to be completed. In a contextual situation, these may have a unit with them. So there may be days, hours, years, minutes, months, weeks, who knows, it could be anything, but it is a unit of time. It is a duration for that activity. Okay, so to perform critical path analysis, what we're going to do is we're going to first of all perform what we call a forward pass. So forward pass, that's the first step. The second step is then a backward pass. And then the final thing to do is to state the minimum completion time and the critical activities. Okay, so that's what we're going to be doing within critical path analysis, within the analysis itself. Each double box will have two numbers in it once we've finished. The left-hand number represents what we call the early start time, and these are the numbers that we fill out in the forward pass of the algorithm. And the right-hand box is the late start time. Late start time, which we will fill out in the backward pass of the algorithm. Okay, so what we're going to do is we're going to first of all locate the start node, which in this case is node number 1. And to start critical path analysis, we're going to put a 0 in the early start time box. That essentially means we are going to start our project at day 0. Okay, we then look at all of the nodes which have arrows going into it from nodes that have already been completed. So for example, node 2, we've got an arrow going into it from node 1, but we also have an arrow going into it from node 3. So I can't complete this number yet because I need this one to have been completed first. Okay, let's look at node 3. That's got one arrow going into it, and that is from node 1. So I can fill out this number because there's only one input into node 3. So the way we calculate this input is we do the early start time of the previous node plus the duration of that activity, and that will give us the number 10. Okay, so number 10 goes in there. That essentially means I cannot leave node 3 until at least 10 days into the project. I'm going to be referring to these as days. So 10 days into the project, that is the absolute earliest time I can leave node 3. Okay. Now that I've got a 10 in there, I can update this node, which I couldn't do earlier because I didn't have that number. But I've got 0 plus 3 is 3, and 10 plus 4 is 14. And in the forward pass, you take the biggest number. Okay, so in this case, that's the number 14. I'm comparing the numbers 3, which is 0 plus 3, with the number 14, which is 10 plus 4, and I'm taking the biggest. That's 14. That essentially is saying I cannot leave node 2, that is, I cannot start activity F until at least 14 days into the project. And that is because activity F requires B and D having already been completed. I could do this one down here as well. I've got two inputs. I've got 10 plus 2, which is 12, or I've got 0 plus 11, which is 11. And again, for the same reason, I take the biggest number on the way forwards. So that is the number 12. Okay, and I just continue in that manner until I complete all of my early start time boxes. So I cannot do this one yet because I haven't got this one. I can do this one because the only input is from node 2, and I have an early start time for node 2. So the number that goes in here is going to be 14 plus 3. Okay, the early start time plus the duration gives me the next early start time, which is 17. I can now do this one. I'm going to compare 17 plus 3, which is 20, with 10 plus 8, which is 18. And I'll take the biggest. Okay, always the biggest on the way forward. So the biggest of those two is the number 20. This one here, I've got two inputs into it. So I've got activity H and activity I, and I'm going to compare them both. So 10 plus 5 is 15, 12 plus 7 is 19, and I take the biggest. So 19 is the biggest there. Okay, and finally, we've got this node here. This one's got three inputs into it, so we need to check all three. 17 plus 12 is 29. 20 plus 7 is 27, and 19 plus 11 is 30. So out of those three numbers, I've got 29, 27 and 30. My biggest is 30. So that is the number that goes in there. Okay, that's the forward pass complete. Just to remind you, in the forward pass, we add the numbers, we take the biggest, and we follow the arrows. Now the backward pass is very similar to the forward pass, except we reverse all of those processes. So instead of adding the numbers, we're going to subtract them. Instead of following the arrows, we are going to reverse all of the arrows. And instead of taking the biggest number, we are going to take the smallest number. But we do start the backward pass by duplicating the number from the early start time here across to the late start time there. Okay, so we want the whole project to be done in the minimum completion time. It takes a minimum of 30 days to complete the project. So therefore I want the latest time to be 30 as well, because then that locks in the whole project being done in 30 days. Okay, so work backwards through the network. Don't forget all the arrows are now reversed. So this node here only has one input, and that's this one here. So 30 minus 11 is 19. So 19 gets put in there. It's only one input, so I've got nothing to compare. Again, this one's only got one input. Okay, don't forget you're reversing all the arrows this time. So L is the only input on the way back. So 30 minus 7 is 23. So 23 gets put in there. As I continue in this manner, I'm taking the smallest number if I have a choice. So node number 5, I've got 30 minus 12, which is 18. And I've got 23 minus 3, which is 20. So I've got a choice of 18 or 20, and I'll take the smallest. So that is 18. Keep going. 18 minus 3 is only one input. I get a 15 in there. This one's got loads of inputs. I'm going to come back to that. This one's got one input. 19 minus 7 is 12. So 12 gets put in there. Okay, now this one, I've got 4 inputs to check. One from node 2, one from node 6, one from node 7, and one from node 4. So 15 minus 4 is 11. 23 minus 8 is 15. 19 minus 5 is 14. And 12 minus 2 is 10. The smallest of those four numbers is 10. So 10 is the number that gets put in there. And then finally, I've got my start node. There are 3 inputs. I should check them all. 15 minus 3 is 12. 10 minus 10 is 0. And 12 minus 11 is 1. The smallest of those 3 is 0. And it should always finish with a 0. Okay, use that as a check. Don't just put a 0 in there and move on. It's got a self-built mechanism for checking in there. Take advantage of it. So 0 is the smallest of those 3. Okay, so now that we've got all of my forward pass values and my backward pass values in my network, it's now time to state what the minimum completion time of the project is and what the critical activities are. So the minimum completion time, I could have done this after the forward pass, but the minimum completion time is 30. Now I'm just going to pop days there in brackets. It might be whatever units it was, might be minutes, weeks, whatever. Okay, so 30 units of time. And then the critical activities, to decide which activities are critical, we are going to look at all of the nodes which have the same numbers on the left and right. So this node here has a 0 left and right. This node here has a 30 left and right. This has a 19 left and right. This has a 12 left and right. And this has a 10 left and right. All of the other 3 nodes, they have different numbers either side. Okay, you've got 14, 15, 17, 18, and 20, 23. So those 3 nodes will not contain a critical path. The critical path will only join nodes which have got double numbers either side. So in this case, the critical path is activity B, then activity E, then activity I, and then activity M. And if you add up the length of those activities, you should find that it equals the minimum completion time. 10 plus 2 is 12, plus 7 is 19, plus 11 is 30. And those are the critical activities. The critical activities are B, E, I, and M. Minimum completion time is 30 days. The critical activities are B, E, I, and M. There are no other critical activities, and we'll get into that in a little bit more detail when we do float in a future video. For example, why isn't activity H critical? Okay. Why isn't activity C critical? And so on. Okay, we'll get to that later. Okay, I've got one more example before I finish up this video. So here we have another network. Okay, a little bit of a bigger network here. And I'm going to perform CPA on this so you can see how it's done in a second example. If you want to pause the video and have a go yourself, then do that now, and then play it again to get the answer. Okay, so to start the algorithm, what we're going to do is just pop these double boxes next to each node. Like this. So the left-hand number is the early start time, and the right-hand number is the late start time of each event. Once you perform CPA. And like I said earlier, it's likely that I'll be given to you in an examination. Depends if they ask you to draw the network or not. Okay, so to start, we're going to do the forward pass. We're going to pop a 0 in the left-hand box of the start node. This is the start node because it's the only node that only has arrows coming out of it. And this is the end node, okay, not node 9, because this is the only node that has arrows only going into it. Node 9, despite being a bigger number, actually has an arrow coming out of it, so it is not the end node. There'll be exactly one start node and one end node for any CPA network. Okay, so on the way forward, this has only got one input, so that's going to be the number 3. This has got 3 inputs, so I can't do that one yet. This has got one input, so that's going to be 0 plus 2, which is 2. This has got 2 inputs, so I've got a choice of 0 plus 3 or 2 plus 4. On the way forward, I'll take the biggest number, so it's going to be a 6 in there. This one's now got 3 inputs, so I can check all 3 of those now. So 3 plus 1 is 4, 0 plus 3 is 3, and 2 plus 3 is 5. So the biggest of those is 5. So on the way forward, we take the biggest number. This one down here has only got one input, so 6 plus 2 is 8. This one here, we've got 2 inputs. We've got 3 plus 5 is 8, or 5 plus 3 is 8. So we're going to get 8 there. Yeah, both inputs are the same. This one's only got one input. It's going to be 8 plus 1, which is 9. And then this one's got 4 inputs, and you check all 4. 9 plus 2 is 11. 8 plus 4 is 12. 2 plus 4 is 6. And 8 plus 3 is 11. So the biggest of those is 12. Okay, that ends the forward pass. And if you wanted to, you could state at this point that the minimum completion time is 12 days, minutes, whatever. Okay, now the backward pass. We are going to duplicate the number at the end node from the left box to the right box, and then we're going to reverse the process of the forward pass. So instead of adding the durations, we're going to subtract them. Instead of following the arrows, we're going to reverse them. And instead of taking the biggest number, we're going to take the smallest number. So this one's only got one input, so 12 minus 3 is 9. This one's only got one input as well, so 12 minus 2 is 10. This one's got 2 inputs, 12 minus 4 is 8, and 10 minus 1 is 9. Take the smallest, so 8 goes there. This one's only got one input, 8 minus 3 is 5. This one's got 2 inputs, 8 minus 5 is 3, and 5 minus 1 is 4. So the smallest of those is 3. So 3 gets put in there. This has only got one input. 9 minus 2 is 7. This has got 3 inputs. So I've got 8 coming that way, 3 coming that way, and 2 coming that way. So 2 is the smallest. And then at the start node, it should be a 0, but don't just write it. Do check it. I've got 4 inputs to check. 3 minus 3 is 0. 5 minus 3 is 2. 2 minus 2 is 0, and 7 minus 3 is 4. So the smallest of those, which occurred twice, is the number 0. Okay, so that completes the backward pass of the algorithm. Now, what nodes are going to be part of my critical path? Well, the start node and the end node, which will always be. This one here is critical, this one here critical, this one here is critical, this one here is critical. All the others are not. There we go. Now the question is, how do we get a path from the start node to the end node which goes to all of those? Okay, so that missed out that one. Nope, that missed out that one. No, you can't go backwards up an arrow. So this is one of those situations where there is not one critical path. We have multiple critical paths. Now, spotting a multiple critical path problem is going to be a bit easier once we have done once we've done float, which will be in a video coming up. But for now, we essentially can break it up into this activity, this activity, this activity, and this activity. But we also have this activity and this activity. So what we've got here is what I refer to as a dual, D-U-A-L, critical path. A dual critical path. Okay, the critical path is dualed. We've got this route here, which goes up through node 4, then through node 3, across to node 6, and then finally down to node 8. And we've also got this critical path, which comes up to node 2 before coming round to join the other critical path at node 6. And we can check the length of all of those from start to finish. So 2 plus 3 plus 3 plus 4, that equals 12, and 3 plus 5 plus 4 is also 12. So both of those paths are critical. We know B is not critical because we've got a duration of 3, but it's between 0 and 5. So it's not critical. Again, that will become a little bit clearer once we do float. So the critical activities then, those are all of the activities which I have highlighted in green. So we've got activity A, activity C, activity F, activity H, I, and activity M. Those are 6 critical activities for this project, and the critical path has dualed. Okay, right, thank you for watching. I think the next video is going to be on dummy arcs, which is dashed lines, and then we're going to have a look at precedence tables and drawing the activity on arc network. Thanks for watching.